medium and large mass. The reason I'm talking about them both here, and I have this little slash thing going on, is that medium and large mass stars both start out the same way upon leaving the main sequence, and then they diverge at a certain point a little bit further, and I'll talk about that when I get to it. But first off, we're going to see something pretty familiar. You know, we're talking about, this is a little small, we're talking about shell burning, right? The first thing medium and large mass stars do when they leave the main sequence, they start shell burning, just like the low mass stars. Now with the low mass stars, I talked about, that's really bad at shell anyway, I talked about hydrogen, helium, and carbon. And I mentioned that some low mass stars may make one or two more shells. But medium and large mass stars always make all the shells that you can with shell burning, right? So you start with hydrogen and helium and carbon, and then, now I'm going to go through all of them, but you don't actually need to know all of them. I would know hydrogen, helium, and carbon, the first three, and I would know the last one, which I'm going to get to. But I am going to just name the rest as I go through them, just, you know, for the sake of completeness. So after carbon, the next one is neon, and then after neon is oxygen, and after oxygen is silicon, and then after silicon is iron, the last shell. Why is the iron shell the last one? Well, it turns out that iron is a very special element. And here's why. So, excuse me. If you recall from a previous lecture, I talked about the proton-proton chain, how it produces energy, because when you have 4 hydrogen atoms, and then you fuse them into one helium atom, one of the funny properties of protons and neutrons is that their mass can be affected by the sort of nucleus and situation that they're in. And that actually, the one helium atom is less massive than the 4 hydrogen atoms combined, which formed it. So what happens to that lost mass? It gets turned into energy, according to E equals mc squared, and that is how nuclear fusion produces energy. So, we could kind of think of a graph. Here's hydrogen, and then here's helium. We can kind of draw a line like this, where like the y-axis of this graph, sort of, is the mass per proton, or per neutron, of something, you know, of a proton or neutron that's in this kind of nucleus. And then the x-axis would be like the atomic number that you would see on the periodic table. So you start with element 1, hydrogen, element 2, helium, then 3 is lithium, and so on and so forth. Right. And so, yeah, this is how it works. Hydrogen fuses into helium, and that produces energy. However, in terms of nuclear reactions that we humans use, we often use the element uranium, which is a lot bigger, atomic number 92, for our nuclear reactions. Things like nuclear power plants and the early nuclear bombs that we built used uranium. But it didn't fuse uranium. Instead, those early nuclear bombs and modern nuclear power plants get energy from nuclear fission. The uranium atom nucleus splits into 2 or more smaller atoms, and that releases energy. Because actually, the uranium has more mass per proton and neutron than these smaller elements that it ends up splitting up into. So this is kind of weird. It's like the relationship has changed. You know, when you have these small atomic number elements, they produce energy through fusion, but these larger atomic number elements produce energy through fission. Now, if you look at this and you think about it enough, you'll realize that this kind of implies that there has to be an inflection point. There has to be a point at which it changes from going like this to going like this. And there is. It turns out that point is iron. Iron is a very special element because it has the lowest mass per proton and neutron of any element. As a consequence, it is impossible to get energy out of a nuclear reaction that produces or uses iron in it, right? Not produces. You can get something out of something that produces iron, but if you fuse iron, you can't do it, right? Because if you try to fuse iron to get to a heavier element, well, now you aren't releasing any energy, because the next ones after iron, they all have a greater mass. You also can't use fission on iron to get energy, like with uranium, because you're also going uphill in the fission direction, right? So when you try to fuse, and stars, when they form this iron-burning shell, they start trying to fuse iron, is the thing that happens. Which is a problem, because when you try to fuse iron, not only are you not getting any energy out of it, if the protons and neutrons in those iron atoms that you're fusing have to get more massive when the fusion happens, that mass has to come from somewhere, right? And just like how the lost mass turns into energy, it's also possible to turn energy into mass, and that's what happens. Not only does the iron fusion not produce any energy, it actively, vacuums energy up out of its surroundings to turn into the new extra mass that it's going to give to all the protons and neutrons in the new nucleus that it's forming. So it's for this reason, with these special properties of iron, that means when a star starts fusing iron, it's doomed. Not only do these iron fusions not produce energy, they actively suck up the energy that the other shells around it are producing. And so when a star starts to fuse iron, its days are numbered, right? In a very short time scale. I could be wrong, but I think it's like a few days. Fusing iron will totally nullify a star's core's ability to produce energy. And now we're going to get what's called a core collapse. I'm going to go ahead and label this real quick. Shell burning. Which, of course, also leads to this star being a giant, as we discussed last time. But when iron starts to fuse, this leads to a core collapse. With no internal energy, the core can no longer hold itself up against gravity, and it very violently and rapidly contracts, collapsing. And this extremely violent process sort of creates a kickback, which causes a supernova. Supernova are ludicrously massive, violent explosions that take the star's outer layers, now in giant form, and shoot them off into like huge shock waves. Medium and large mass stars never produce planetary nebula like low mass stars do, because they go through their various shell burning phases much faster than the low mass stars, so they don't stay giants long enough to form planetary nebulas. But back to supernova. Supernova are so bright that when one happens, it rivals the brightness of the entire rest of the galaxy it's in put together. We know this because we've seen supernova happen in other galaxies, and we can see that it's almost as bright, that one star going supernova, almost as bright as the entire rest of the galaxy put together. It's nuts, right? But then what's left? Like with the white dwarf, the core is left over after all of the outer layers have been blown off in the supernova. But what happens? Well, this is where the medium and the large mass cases diverge. I'm going to talk about the medium first. Now, in medium mass stars, their cores are massive enough and have a strong enough gravity that they are capable of beating the electron degeneracy pressure that holds up white dwarfs. And so, they become an object known as, I don't know why I'm trying to draw it, known as a neutron star. Neutron stars are ludicrously dense. Like, to give you an idea of how dense neutron stars are, if I could be wrong about this like analogy, but I don't think so. I think I'm right. If you had a teaspoon of neutron star material, it would weigh as much as like a huge 18-wheeler truck. They're incredibly dense. And the reason is that since they've beaten electron degeneracy pressure, they've sort of ejected all of their electrons out. And so the neutron star is basically entirely made up of nuclei, right? Just protons and neutrons. But an atom is mostly empty space, right? The nucleus is the overwhelming majority of the mass of an atom, but it's a very small amount of the actual space that the atom takes up. Most of the atom's space is filled out by the electrons. So when you've shot all the electrons out, and you've just got nuclei left, it can get very condensed, very compressed indeed. Neutron stars are held up by something called the Pauli exclusion principle. I'm not going to get really in detail about what the Pauli exclusion principle is. Basically, it's very similar to electron degeneracy pressure. It acts on different things, neutrons, I think, and it's stronger, but conceptually very similar. Yeah, neutron stars have other crazy properties, like they spin like hundreds of times every second. They have super strong magnetic fields, all kinds of wild stuff. So that's the fate of medium mass stars to become a neutron star. But what about large mass stars? What about large mass stars? Well, large mass stars, during their core collapse, have enough mass enough gravity to even beat the Pauli exclusion principle. Now, when you've beaten the Pauli exclusion principle, there's basically nothing left after that. Having beaten the Pauli exclusion principle, there's nothing keeping the large mass core's gravity from just compressing it into a smaller and smaller and smaller space forever, right? There's nothing can stop it once it's beaten the Pauli exclusion principle. And that is what creates a black hole. Black holes are truly insane objects. They have so much mass, often many times the mass of the sun, that are focused into a point. Because, again, there's nothing stopping them from just compressing the mass more and more and more at this point. And this creates some truly crazy effects. For instance, if you think of gravity, we've been thinking of gravity in this class the way Newton did, as a force between two objects with mass pulling them together. But if you think about gravity the way Einstein did when he formulated general relativity, or just relativity in general, you'll think of gravity, as being a warping of the fabric of space. If you think of gravity as a warping of the fabric of space, black holes have such powerful gravity that they functionally tear a hole in space, right? Black holes are well known for their event horizons, which is like the distance past which nothing can escape from a black hole's gravity, not even light. Now you may think, well, light doesn't have any mass, so why is it affected by gravity? Well, again, you're thinking like Newton. If you were thinking like Einstein, you could think, oh, well, if gravity is a warping of space and light moves through space, it would make sense that gravity could affect the way light moves. Which, yeah, that's how it works. But in the case of black holes, they've warped space so much that not even light can get out of there, past their event horizons. Yeah. So yeah, that's the divergence, and I think that about covers stellar evolution for medium and large mass stars. In the next video, I will be talking about a little bit of a special case, which are companion situations, so we'll see about that.